Albert Einstein is one of the greatest scientists in history. His theory of relativity filled the gaps in Newton's work and explained the nature of gravity. The theory of relativity rejects the notion that it is a force. But if gravity isn't a force, then what is its true nature? Einstein was captivated by the persistent blind spots in Newton's theory of universal gravitation throughout the 19th century. As measurements become more precise, astronomers have mapped the planets observed beyond Mercury and Uranus, continuously deviating from the trajectory predicted by Newton's mathematical formula. Initially, they theorized that undiscovered planets were exerting gravitational forces and pulling along rogue planets out of their orbits, and they were right in the case of Uranus. On September 23, 1846, astronomer Johann Gottfried Galle officially confirmed the existence of the planet Neptune, a landmark discovery based on the independent mathematical calculations of Urbain Le Verrier and John Couch Adams. Neptune was found very close to the position predicted by Paris Observatory astronomer Urbain Le Verrier. This is the first time the existence of a celestial body has been predicted through calculation. In other words, this is the first time astronomers have hypothesized the existence of a clump of dark matter, an entity that has never been directly observed, but is only known through its gravitational influence on surrounding celestial bodies. The successful discovery of Neptune spurred a series of lively activities to find the planet that scientists are convinced is the cause of pulling Mercury off its orbit. Astronomers are confident in the existence of a planet located in the space between Mercury and the Sun, to the point that they even named it Volume Con. However, in reality, there is no planet named Vulcan whatsoever. Perihelion is due to another effect of gravity that Newton. Only when attempting to explain the nature of gravity did Einstein accidentally discover the precise cause of Mercury's anomalous motion. The concept of a continuous space-time continuum is a testament to Einstein's supreme intellect. To put it in relatable terms, it's like a vast scale stretching out through space in every direction, incorporating time as the fourth dimension. In Newton's theory of universal gravitation, space and time were both regarded as rigid, absolute, immutable frameworks, and as two concepts entirely independent of each other. According to the theory of general relativity, space and time combine to form a single, continuous, and malleable continuum. Spacetime can be stretched and warped by the presence of matter and energy. The curvature of spacetime simultaneously affects both time and space, leading to numerous complex consequences, a prime example of which is the phenomenon of time dilation. Einstein used the concept of a continuous spacetime continuum to explain gravity. That it is an effect produced by the curvature of spacetime in the presence of matter. Imagine a rubber sheet stretched horizontally with a heavy object placed on it. The heavy object placed on it caused the rubber sheet to sag, forming a depression. Any small object nearby will slide into the depression, spiral around, and ultimately merge with the heavier object. This is similar to how gravity works. According to this scenario, this two-dimensional rubber sheet plays a role analogous to the four-dimensional continuous medium of spacetime. Matter tells spacetime how to curve, and spacetime tells matter how to move. And without time, matter would not know how to move. So where is the inflection point in our universe? It is difficult to clearly explain this point using this theory. That curve must exist within a dimension that we cannot directly perceive. We are usually only familiar with the three spatial dimensions: length, width, and height. Einstein regarded time as the fourth dimension, and even demanded that we accept that. Gravity is caused by the curvature of spacetime, but this curvature itself occurs within another spatial dimension. Although this Wednesday afternoon cannot be clearly seen, but we perceive it as a force acting upon ourselves and call it gravity. In practice, it is quite similar to centrifugal force. This effect is created during rotation, which we initially addressed in the section about planetary formation. When sitting in a car that is making a sharp turn, centrifugal force creates the sensation that we are being pulled outward, despite the feeling that some invisible force was trying to pull us out of the car. But in reality, it's just an illusion created by inertia, the body's reaction to a sudden change in direction of movement. Our bodies always tend to maintain forward motion in a straight line. But the car was pulling us in a completely different direction, and we feel that change distinctly, as if an invisible force is acting directly upon our very being. Just imagine. The car is being driven remotely, while all the windows are completely covered. Now, we can no longer rely on the external space to perceive our own movement. We had no idea that the car had been hotwired. Within ourselves, it is difficult to recognize what we are trampling upon. I could only feel the centrifugal force pulling me away. This method is often used to heighten the sense of suspense and drama in haunted house attractions at amusement parks. Our carriage suddenly lurched sharply to one side as we rounded a tight bend. Similarly, according to the special theory of relativity, we feel gravity because we are moving along the curvature of spacetime, within a dimension that we cannot directly perceive. A principle that is closely related and plays a key role in the theory of general relativity is the equivalence principle. The case of uniform motion cannot be distinguished from that of acceleration. As early as the 16th and 17th centuries, scientists studying death had recognized this similarity. Galileo Galilei demonstrated that an object's speed of fall is independent of its mass. He demonstrated this by having balls of different masses roll down inclined planes, and noticed that they always hit the ground at the same time. He correctly explained that a feather falls slower than a stone. It's not because it has less mass, but because its structure is better supported by the air. Apollo astronaut Descout demonstrated this perfectly on the Moon in 1971. When dropping a hammer and a feather at the same time, in a place with no air resistance, a feather will fall at the exact same speed as a hammer, even though it is much lighter. And both touch the surface of the Moon at the same time. This shows that not only objects of different masses, but even objects with different structures influence and accelerate each other through the gravitational field. In 1907, Einstein expanded his research on the equivalence principle between gravity and acceleration. This was perfectly illustrated by a famous thought experiment involving an elevator. Imagine we are in an elevator. The space is completely enclosed, without any windows. When the elevator is stationary at any floor, the gravitational force acting on us is exactly the same as when we are standing on the floor. If someone cuts the cable, the elevator will fall, and at that moment, we will feel completely weightless. Any slight movement of the body causes us to float across the floor's surface. Because we are falling at the same rate as the elevator, astronauts experience a similar sensation when orbiting in space. Inside a free-falling elevator, we would continue to float until impact, and the outcome of this experiment would be utterly catastrophic. Now, try to imagine putting a similar elevator into space. To escape from any gravitational body. This time, we will feel as if we are floating adrift, with no gravity acting upon our bodies. And I floated in space at the same velocity as the elevator. This is entirely analogous to the phenomenon of an elevator falling within Earth's gravitational environment. If locked inside, we cannot distinguish between these two situations. Finally, try to imagine this. We attach a rocket engine to the bottom of the space elevator and fire it up. The elevator accelerates, but inertia makes us feel as if we want to stay in our original position. So I stumbled into the elevator, and then it helped me accelerate until I matched its speed. For me, this feeling is identical to experiencing the gravitational pull while standing in an elevator on Earth. The faster the speed increases, the more pronounced the sensation of gravity becomes, as if experiencing an extremely powerful, immense gravitational force. In practice, this force is commonly referred to as drag and occurs on all aircraft or rockets moving at high speed. The equivalence principle is succinctly illustrated by the results of the thought experiment involving an elevator. It is impossible to distinguish inertial forces from a gravitational field. Only when Einstein accepted this did the general theory of relativity become complete. His predictions also align with Newtonian gravitational calculations when the gravitational force is weak. According to the theory of relativity, this phenomenon occurs when the curvature of spacetime is shallow. However, when gravity becomes stronger and spacetime is more significantly curved. General relativity introduced new adjustments in the description of gravitational forces acting on celestial bodies. This is how Einstein explained the anomalous orbit of Mercury. Unlike other planets, Mercury is sufficiently close to the massive Sun, making the curvature of spacetime an extremely significant factor. And we need general relativity to accurately calculate its motion. This is a necessary but insufficient success of Einstein's theory. Addressing a known problem is a meaningful endeavor that contributes to reinforcing a theory's credibility. But checking whether that theory can predict entirely novel phenomena is precisely the crucial issue. Einstein could have solved this problem too. According to his own theory, he realized that gravity could bend the light from stars at a much greater angle than Newton's calculations had suggested. The problem is, how can you prove that? According to Newton, gravity only acts on objects with mass, while light is a form of energy that has no mass. Therefore, he believed it could pass through the gravitational field with almost no effect. However, Einstein predicted that light following the curvature of spacetime was an obvious fact, identical to the orbits of planets and moons. His calculations showed that when passing through a gravitational field, light would be deflected from its original path. Like a golf ball that touches the edge of the hole and bounces out. This concept is known as gravitational lensing, and more detailed calculations later revealed that the only object in the solar system capable of bending light from stars is the Sun. The only time astronomers can observe the stars near the Sun is during a total solar eclipse, when the Moon completely blocks its dazzling light. In 1919, Arthur Eddington led an astronomical observation on the island of Principe, an African island in the Atlantic Ocean, to perform the necessary measurements during the upcoming solar eclipse. Although the morning was cloudy, the sky cleared up just in time for the most impressive total solar eclipse. As nightfall descended abruptly, Eddington swiftly proceeded to take photographs, precisely recording the positions of the stars on the photographic plates, and compare them with the photos taken just as the Sun emerged from behind the mountains. He discovered that these stars had shifted significantly from their previously calculated positions. Just as Einstein predicted, light can be bent when passing through a strong gravitational field. There is no doubt that the theory of relativity has been proven correct. When this news was announced, Einstein suddenly became a global celebrity. However, this brilliant success also brought with it consequences for modern physics. Nearly a century has passed, yet we still cannot apply the explanation of gravitational force. According to the general theory of relativity, other natural forces are also described. If we could do that, we would probably have a theory of everything by now. If we include gravity, there are naturally four fundamental forces. First and foremost, one must mention electromagnetic force, a concept that has become extremely familiar. All known electrical and magnetic phenomena have been explained, and it has been thoroughly exploited by science and technology since the late 19th century. The early 20th century witnessed the discovery of two other fundamental forces. When physicists delve into the study of the atomic nucleus, these two nuclear forces, the strong and the weak, are quite abstract and difficult to visualize. The strong nuclear force is the force that binds protons and neutrons together to form the atomic nucleus. And to break a nucleus apart or combine two nuclei together, it is necessary to overcome this binding force. Therefore, the strong nuclear force is the key factor that enables the release of energy from stars and the splitting of atoms. The weak nuclear force is responsible for certain types of radioactive decay. If considered a fundamental force, gravity is the weakest of these forces. This can be easily demonstrated by observing the nail being attracted and lifted by the magnet. The magnetic force generated by a magnet can overcome Earth's gravitational force. However, on the largest scales of the universe, it is gravity that governs the expansion of spacetime. This is because this force acts over a very long distance, while other forces have a very limited range of influence. The two types of nuclear forces only exist and act within the range of an atomic nucleus's size. The electromagnetic force, although it has a longer range of action. However, this trend can be negated when the distance is too large, as both positive and negative charges exist simultaneously at that point. The repulsive force between like charges and the attractive force between opposite charges both increase. Physicists can explain phenomena related to electromagnetic force. And these two types of nuclear forces are formed through the exchange of extremely tiny particles, with an exceedingly short existence, known as virtual particles. On the other hand, gravity can only be explained as a consequence of the large-scale curvature of space. Many physicists remain both skeptical of and hopeful for perfect symmetry in their theories. Ultimately, gravity will be officially recognized as the fourth fundamental force, in which the exchange of minuscule virtual particles called gravitons takes place. If this is proven, the curved space in Einstein's theory of relativity would become a scientific metaphor. Helps to better visualize gravity before the official answer is found. The leading candidate for unifying gravity with the other fundamental forces is string theory. This theory replaces atomic particles with minuscule, vibrating strings, and use them to constitute all particles in nature, including the graviton. String theory has expanded Einstein's idea of additional spatial dimensions through vibrating strings that traverse additional dimensions of spacetime. We only see those strings as tiny dots, because we cannot perceive the other dimensions. However, no matter how confident one is in string theory, there is undoubtedly still a very long road ahead. Only young scientists could prove that. The operations are so complex that even experts are still struggling to connect the ideas. For phenomena that can be observed through experimentation and verification. Therefore, the quest for a theory that can unify gravity with the other fundamental forces of nature continues. it remains as intractable as ever. The disparity in size between the ultra-tiny virtual particles and the empty regions of spacetime appears to be too vast. A new approach is needed to bridge this gap. And in the meantime, physicists and future generations, searching for any discrepancies between the predictions of general relativity and reality, and what can truly be observed. This difference is analogous to comparing the actual motion of Mercury with the predictions based on Newtonian mechanics. They will pave the way for new understandings of gravity. Perhaps this aligns with our understanding of the other fundamental forces. The problem is that, to this day, no one has been able to find any difference. Einstein believed that his theory might no longer hold true in cases of extremely strong gravitational fields. In the 1950s, scientists discovered a class of celestial objects capable of generating incredibly powerful gravitational fields. That era witnessed the remarkable development of both radio and telescopes. And Joost Lindbell, a student at the University of Cambridge, scientists have detected a radio signal that clearly originated from outer space. Because it always appears in the exact same position in the sky every night. The signal blinked on and off steadily and rhythmically, like a clock. She named it the LGM-1 source, a playful yet serious abbreviation of the name Leto Greenman. However, it was not long before theoretical physicists demonstrated that is most likely the spinning super-dense remnant of an exploded star. Such a neutron star is even smaller in size compared to a white dwarf. While white dwarfs are only about the size of Earth, they possess a mass nearly equal to that of the Sun. A neutron star is only about the size of a small asteroid. Its diameter is approximately 10 to 20 kilometers, but its mass is several times that of the Sun. A neutron star is entirely composed of dense matter, with a density equivalent to that of an atomic nucleus. Therefore, it has an extremely high density and an immensely powerful gravitational field. Astronomers who specialize in studying radio waves often call these stars pulsars. Because when a neutron star spins, it can emit extremely powerful radio waves, sweeping across the universe, like the light from lighthouses ever shining. The radio signal appears as a continuous on and off pattern when scanned across the Earth's surface. In 2003, an important discovery was recorded: the binary twin star, a phenomenon of two twin stars orbiting each other. This pair is particularly notable because the distance between them is only 800,000 kilometers. That distance is nearly 90 times shorter than the distance from Mercury to the Sun. And they take only 2.4 hours to complete a full orbit around each other. Einstein predicted that in such an extremely powerful gravitational field, objects moving in orbit will gradually lose energy, and this energy will continuously radiate into the surrounding spacetime environment as gravitational waves, much like ripples spreading across a pond. By measuring the orbital period of binary star systems, astronomers have calculated the amount of energy the binary star system is losing. They discovered a value, and that value perfectly matched Einstein's theory. At the very least, the accuracy is on par with the telescope's measurement capability. The stars are moving 7 millimeters closer to each other every day. As the distance closes, the energy delivered to the target also increases. Finally, in about 85 million years, these two stars will collide. A cosmic flood of gamma rays submerged a large part of the Milky Way. General relativity accurately predicted the energy loss mechanism of pulsars. This is yet another fantastic piece of news confirming Einstein's theory. However, for physicists, this is not very encouraging. Hoping to find a new clue to elucidate the nature of gravity and how it relates to other forces in nature. Most modern tests of general relativity focus on verifying the equivalence principle, hoping to find a difference between the effects of gravity and acceleration in a non-inertial reference frame. The principle of relativity is only valid within the scope of the general theory of relativity. According to string theory and several other scientific hypotheses currently being explored, to unify gravity with the other fundamental forces, equivalence only needs to be achieved at a level of accuracy that is sufficient. With measuring devices of sufficient sensitivity, that is entirely possible. We can detect the deviation. One of the most promising experiments has been conducted over the past 4 decades. Thanks to the successful Apollo missions that landed on the Moon. Its name is the Lunar Laser Uplink. The Moon is an excellent laboratory for studying gravity, an experimental mass of colossal size, located sufficiently close to Earth to be accessible. During the observation process, astronomers at the Apache Point Observatory, New Mexico, an extremely powerful laser beam was fired directly at the Moon. They aimed and fired at the reflective targets, which were about the size of a suitcase, placed on the lunar surface.